you got standard cooling, standard heat rejection. You got a set of pumps pumping out to a fluid cooler. You might have a boiler down here. And I mentioned the other day that the boiler is probably a sidearm boiler, doesn't necessarily have to have all the flow. You go down here to your heat pumps. There's my pump, air separator, boiler, heat pumps, fluid cooler. Okay, normal operating, this operates similar to like a coolant tire, so I can probably produce something like 90-degree water here with 100-degree water coming in. So my range is going to be 100 to 90 degrees during the cooling season. So I'll send out 90 degrees to all the heat pumps, and it's coming back at about 100 degrees. Okay. Someone was asking about the temperatures. I can select a heat pump like this and probably produce 58-degree supply air right here in the cooling mode. And in the heating mode, and these systems, you know, this is a single pipe or two pipe system. You got a supply and return. Summertime, I'm trying to maintain, everything's cooling. I'm trying to maintain 90-degree water. In the mild season, I got an interior unit that wants to cool, an exterior unit that wants to heat. And it's the range, the wintertime range, this boiler might want to produce 140-degree water, but I'm only going to take enough water off the boiler to mix with probably 60-degree return air and produce maybe 68-degree to 70, we'll just round it off to 70 degrees. 70-degree air. So my range of my piping system is actually 100 to 60 degrees, depending on the time of year. If I'm full heating, everything's absorbing heat out of the loop for the compressor. I'm operating this range. So I'm going to operate somewhere in the seasons between 100 and 60 degrees. The loop will be operating in that temperature range. So with a see, I can produce in the summertime with 100-degree air, 100-degree water. I can produce about 58 degrees right here. Cooling. All right, in the wintertime, if I'm operating at 60 degrees, I can produce about 96-degree air. If I'm heating, I can produce about 96-degree air with 60-degree water. Now, if I make this, if I lose my boiler, I make this geothermal. In the geothermal system, you don't normally have a boiler. And this becomes a ground loop.
I've got a question here.
Okay?
Say in the summertime, you want, you got 100-degree water coming?
I can have up to 100-degree water.
Oh, up to, okay. All
Up
right.
to.
Okay, that's supposed to be hot, ain't it?
Yeah. Yeah, but it depends on what type of fluid cooler I'm using, is what I can actually produce, or if I'm on a ground loop. If I'm on a ground loop, I may be up to 100 degrees. So I've got a series of loops in the ground. Some kind of ground loop out here that I might get down to 40 degrees in the wintertime. And 40 degrees in the wintertime, I'm producing 85 degree air right here. Your skin temperature is thinking about 90, 88, 90 degrees. Anytime you get below that skin temperature and you blow air on it, it feels cold. So now if I were producing, if I had a boiler or my loop was operating the way I want it to operate, say I could maintain 55 degree in the winter, and all of a sudden I'm producing 96 degree air again. So in a geothermal system, depending on your application, if it's residential, probably want to add supplemental electric heat. But it just, again, depends on what kind of ground loop that you've got. If it's a pond, if it's a ground loop, is it adequately sized, is it undersized, is it saturated, been there 10 years, the water's gone. Those are the things that you get into. Now, in the loop has to be self-balancing. So you want to try to do the reverse return system to where first in is last out, and last out is first in. That's actually, I got it reversed here. I don't have it drawn 100% correctly. But there's a method that you can route this ground loop to where the loops will be actually self-balancing. Talk about fluid coolers, spray coolers, difference between what I call a spray cooler and a coolant tower. Most people use an evaporator fluid cooler. So you'll have a some form version of a coolant tower box, sheet metal box, blower off the side. These come in centrifugal versions and axial versions. When we talk about axial fans or the propeller type fans that would sit on the side of the box like that. They come different versions. You'll have sometimes a discharge damper right here. You'll have heat exchanger. Comes in. This is galvanized or copper heat exchanger. It fills up the whole box. Then you'll have a spray pump sitting in here, and you'll have a basin full of water. That basin full of water has got to be chemically treated to prevent biological growth. And this spray tree come up here, the distribution system, and just spray water over the heat exchanger, and then you can operate, generally produce about 90-degree water with 100-degree water coming in. That's would be called the fluid cooler. And we talked about this is a supply to the heat pump system. This is the return coming from the heat pump system. And you might have thermometers out here, display. You might have temperature test port, isolation valves. And that generally your full fluid flow goes through that heat pump all the time. So in the wintertime, I'm pushing water through here, so I close these dampers. So I try to maintain heat. First stage might be spray pump over the heat exchanger, running water through there. Second stage might be bringing the fan on. And like I said, I can produce about 100-degree, 90-degree water with 100-degree return coming back in. And that's, again, that's at the extreme condition that everything's heated. Again, the heat pump loop is going to operate in that range from 60 to 100 degrees. And on the boiler side, our pump coming in here, we're sending water off to the fluid cooler. We'll have a boiler in our water source heat pump system. We're going to take enough water off of here with the pump, put it back in. I've got a temperature sensor right here. And maybe a temperature sensor right here that says, hey, I'm at 59 degrees. So I'm going to turn the pump on, activate the boiler. The boiler is probably going to produce 140-degree water. It's going to mix with that 59's here, 59's here. What I may have to do with some type of boiler, I may actually have to have a little bypass right there. It takes some of the hot water, mixes it with this water, heats the return back up to prevent the boiler from condensing. This might be just a small sidearm flow right there, but most of the water is going to go here and mix 140 with 59. Make 70-degree water, which is maybe what I want to maintain as a minimum supply water. So that's how the boiler system works in most cases. Now what I could do is take that pump, take off to the boiler, and run it through a flat plate heat exchanger or some sort of heat exchanger, tubular. This goes out to my heat pump system right here. This is from the heat pump system. Now I've got a heat exchanger. Well, on the other side of the heat exchanger, I can still have 90-degree water here and 100-degree water here, because I've got a cooling tire, standard conventional cooling tire. This is cold. I've got to introduce another pump. So I'm producing 85-degree water here with my cooling tire, and 95-degree water here. water's going like this. Actually, that'd be counterflow operation. These would be backwards. 85 here. 95 here. But I can get a 5-degree approach on that heat exchanger pretty easily, where I can produce 85. Actually, I might even be able to get that even closer. If I've got 85 up here, I could probably get that even down maybe to 90 with a flat plate heat exchanger. And anytime I can get this water temperature lower, I produce my compressor lift. So on the boiler, so there's the coolant tower. This way, I've got my standard basin here, but in the wintertime, if I know I don't have any simultaneous heating and cooling, I can shut this down, or I can put a basin heater in here. You don't have to worry about freezing. This is inside the building. Again, you might put thermometers on both sides of this just to visually check it. Pressure temperature taps so that you can check it with gauges and temperature. Okay. Standard system. Well, I've got some type of heat rejection. Heat pumps, heat pumps, heat pumps. Heat, or system here. Pumps. In return. So that's the benefit of the water source heat pump system, is I've got a common loop out here that is operating from 60 to 70 degrees, so I don't need any insulation. Piping can be steel, copper, PVC. Any one of these units can heat or cool at the same time. That's probably the benefit to the water source heat pump system. And if I'm heating, if I'm in the heating mode, that means the compressor is actually absorbing water, absorbing temperature out of the loop. So I'm coming in at 70, going out at 60 or 67. If I'm cooling, I'm coming in at 70 and going out at maybe 78 or 80 in the mild season. So you can see if you got simultaneous heating and cooling, you don't necessarily need any heat rejection or heat of absorption. Still got the standard, we talked about the standard piping system, makeup water, air separator, expansion tank. That's no different than a chill water system. We were talking when we left the other day about boilers, heat rejection, hydraulic accessories are the same as any other piping system. Controlling the system. I'm supposed to talk about controls. Heat pump selections, where we kind of left off the other day. Talked about geothermal and water source heat pumps. Water source heat pump uses a, we're talking about a or refrigerant flow diagram where I got a compressor. I come off that compressor to a reversing valve. And that reversing valve is either going to send refrigerant from the evaporator coil, from a condenser, and from the condenser we go okay. So if this is the compressor, and the evaporator back into, let's get back to all this stuff. Okay, condenser, evaporator, reversing valve. So the compressor's pumping this direction, going through the reversing valve. It's going to send refrigerant back to the condenser, into the evaporator, and then back to the compressor in cooling mode. Okay? So your refrigerant flow is here, hot gas, into the reversing valve, into the condenser, which is a water-cooled to refrigerant condenser, into here, through some type of distributor, back to the reversing valve, back to the compressor. I might, in a geothermal application, I've got to insulate the condenser and add an expansion valve right here. That's the difference between water source, no insulation, only a distributor or orifice. I go into geothermal application, add an expansion valve, and I insulate the condenser. Now if we go to heating, what happens is I'm still coming off, should be using red, the condenser going through the reversing valve, then I'm going to go to the evaporator, and I have a bidirectional expansion valve, meaning the expansion valve is actually designed for refrigerant flow in both directions. Go back to the condenser, up to the reversing valve, and back to the compressor. That's the basic reversing application or reversing valve heat pump application. That's how we able to either heat or cool. Does everybody understand that? The use idea of the reversing valve? All that does is it's an electrically operated device. I got a thermostat that either puts my compressor on in the cooling mode or the heating mode. And the thermostat actually controls the reversing valve between whether you get heating or cooling in this application. And that's just a little electric valve. Some of them actually, the reversing valve actually is just a plate right here where your hot gas might come in here and your refrigerant back to the suction might go back to the compressor here, and then you either send it to the evaporator or send it to the condenser right there. And it's basically just a little slide valve that goes back and forth. Okay. Then I might, if airflow is, let's say this direction is air, and I might introduce another coil right here that is hot gas reheat or humidification. For instance, if I'm putting all my outside air in the heat pump, I might have some needs that I might have to dehumidify because my cooling load is satisfied, but I'm putting in a constant amount of fresh air all the time. So there's not any cooling demand other than drying out the outside air. So I introduce hot gas, then I take this, then I introduce another valve here that puts the hot gas back into this thing, and then we go back into our suction line from the hot gas. Okay. We were talking about size, and the last thing we're talking about size, and we kind of left off last week for size of the boilers. But I've estimated my load at 60 tons for the building. But these are all incremental equipment. I've got a space here that requires 2.3 tons. I'm going to put a 3-ton heat pump, and it goes on and on and on. So my connected load might be 80 tons. Connected load. Okay. Then I take my building heat divided by the installed capacity, that gives me diversity. So I've got a diversity, what's 3/4, right? So I've got a diversity of 0.75. And then diversity times delta T plus air and water. So take the diversity. I've got a size of my system on a delta T, 10 degrees. You know, we talked about 90 degree into the fluid cooler and 100 degree out of the fluid cooler. So I've got a 10 degree delta T. So if I take that times my diversity factor, which is 0.75, so I actually end up with a 7.5 degree delta T. Plus my area water temperature of 90 or 80, whatever it is. So I ended up, I can actually select I've got a 60 tons, so I've got 180 GPM maybe as my flow. And I want a 7.5 degree delta T, so 180 times 7.5 times 500 is equal to BTUH. There's how I size my fluid cooler. So I don't have to just use a 10 degree because I've actually got diversity in my system. So my load is 60 tons, and with a heat pump system, I'm not just going to actually size that fluid cooler on 60 tons. So I take my connected load, divided by my actual building load, come up with a diversity. I have selected a 10 or arbitrarily 10 degree delta T. Time my diversity factor gives me 7.5. I know what my flow is required for each heat pump. So GPM times delta T times 500 equal BTUH. So that's how I size my cooling tower. You go through a similar process sizing the board using your heated load, your connected load of the heat pumps, times the diversity factor, times delta T, same thing, selected board. I wouldn't, there's a lot more into it, but that's basically how the equipment is sized. I wouldn't, it takes a little bit more information than this just to go through the process. But it's not like a chiller. I guess that's just what I'm trying to say. If I've got 100 tons in my building, I select a 100-ton chiller. So there's a little process using diversity, and what your heat of absorption or heat of rejection is in selecting the fluid cooler or the boiler.
Steve, the difference between the load and the connected load, again?
Well, my load is what I calculate. And my connected load is actually the equipment that I'm putting in. For instance, like I said, this room might be 2.3 tons, but I got to put a 3-ton or a 3.5-ton heat pump in it because I don't have a 2.3-ton heat pump. And that just multiplies as you go through the building. Very seldom are you going to be able to match your connected load to your actual building load. And also, there's a safety factor that always people put in there. Now, no one's ever going to undersize their equipment. If you did, then your diversity factor would be 1 or greater than 1. Anything else? What I thought we'd do next week is kind of take a piping system, a complete overall piping system, and digest it. Talk about how pumps are sized, how pressure drop is calculated to the piping loop, and what the heat exchanger or air separator actually, how it functions, how the expansion tank actually functions. Kind of go into that piping system that we talked about when we went through an overall chill water system, and just kind of go to it in a little bit more detail and show you how the pump is selected and the pressure drops through the system, where the major pressure drops are. Elbows and pipe lengths are nothing compared to strainers and check valves and chiller barrels. So I'll just show you a few numbers and give you some magnitude of what chiller barrels and check valves and strainers are versus 1,000 feet of pipe and 200 elbows. All that pipe may be actually less than your fittings. So I'll just show you some numbers, and we'll kind of run through the selection of how you select the pump, and then maybe show a little pump curve in greater detail than what we did before. Apologize for not being able to get this up, and let you see some pictures here that I've got.
Computer just didn't want to get out of bed this morning.
Well, no, we've been having problems with this wireless setup and that new, this is a new projector. Notice we got our lights on. We bought a projector with a higher wattage, and but we're having problems communicating to it. Okay, appreciate it. Size it is, and most of these loops are 3/4 of an inch vertical piping. Horizontal is whatever it takes to get all your loops together. Some of these series loops, you got to be careful about how many you put in series again, because most of this is 3/4 of 1 inch piping.
Do you get water down there?
Well,
Is that plus or not?
plus is hitting water. So this is your well. They drill a 6-inch well, and this is a packaged roll of pipe with a typical, very close coupled U-bend connector on the bottom of it. They push your pipe down there with grout, and the grout is very important because it is your heat exchanger back to the ground. So there's a special type of grout they use, bentonite or some other type of driller's mud that they use for grout that uses the heat exchanger. And so generally it's a 4 to 6-inch well that's being drilled 250 to 500 foot deep.
Do they always get water, or they just open it up?
No, what you normally do is in a test well, or if you're going to do a geothermal application, you come out and drill 1 or 2 wells. And they test the ground. They actually heat the water up, put it in the ground, and put it back up to have a heat source. And they're testing the conductivity of the ground to see what kind of heat rejection or heat absorption they can get out of the ground. The ideal ground is rocky with water flow through it. If it's a rock ground, water flow going through it, you have an incredibly good heat exchanger. Incredibly good heat exchanger. If there's no water flow through the ground and it's purely sand or dirt, then there's really no heat exchange. I mean, you're going to get what's called I can't remember the terminology, but you're just heating the ground up, and eventually your loop goes bad.
They like a dead air pipe again.
Yeah. Yeah. So ideally, You get high conductivity when you have water flowing through the ground.
Well, not putting it in the lake, Steve.
There are applications where you can buy stainless steel heat exchangers and put them in the lake, or you can actually drop these pipes into a lake. There are other applications called slinkies. What you have to do is you build actually a jig, maybe out of 2x4s or 2x6s, and the designer tells you to take a piece of 3/4 inch or 1 inch tubing and start coiling it like this. And you'll get a specification that says what that dimension has to be and what this dimension has to be. And you just wire tie the pipe together. That's called a slinky. Generally, they'll run up to 500 foot in length.
Whoa.
Right down in Texas, the Colorado River, they actually, had where the pipe went down into the river itself, had to have a screen on the end, to keep the trash out, but, in fact, that was one of the problems of the airflow, or the water flow, every now and then that screen would fill in.
Yeah. Now, the third method, this is generally in a horizontal ditch. So I've got a ditch that's generally 5 foot deep to 7 foot deep. And this slinky is laying in that ditch. This is vertical well application as well as horizontal well application. I can dig the same ditch and put my supply and return pipe in it in horizontal application. Generally, your piping lengths might be 60% more in a horizontal application because, again, you're not getting quite the conductivity as in a vertical well. This can be in a horizontal ditch. It can be laid in the bottom of a pond. The other method for geothermal is a supply and return well. It goes into my heat pump. That's a pump down in a well. And then you reject it back to another well. That's an open loop system. So you got to have a heat exchanger that's capable of the corrosion that's going to be caused by that open loop system. And they do, and most manufacturers do make a special heat exchanger for what's called open loop systems. But this is your supply well, might be 250 foot deep. You're getting down to a water table. And you're actually supplying water just like your domestic water well at your rural house. But then you got to put that water back in the ground someplace.
What would be the advantage or disadvantage of that particular system?
Constant 50-degree water.
Always in cold water.
Okay.
25 EER in summertime. So this is what I have in my house. And my return well is my septic tank. Because I don't have any kids at home anymore. Nobody's showering 6 times a day. So I got an adequately sized leaching field that can take that much water and put it back in the ground.
Question. So you're actually, that system right there, I see what you're saying, that pump is actually pumping water from the
Yeah,
ground
this is
itself.
just a typical well submersible pump.
Okay, and then, all right, that's by the, okay.
And I'm just taking the groundwater and running it through my heat exchanger, and I'm putting it back into a well or some method to get it back in.
Okay.
So when your unit calls for heating or cooling, that energizes that pump?
Yeah. Yeah, well, actually, I got a pressure tank here that with a pressure switch maintains a certain pressure.
So when your valve opens to your heat exchanger,
I got
pressure
pressure.
drives, pump starts.
Yeah, so
Okay.
the pressure switch starts the pump.
What pressure do you run that at?
It's typical domestic water, 50 pounds.
Okay. So you actually run it that high?
Yeah, it wouldn't have to be that high.
Okay.
Steve, you see a lot of that in commercial applications?
Not in commercial applications, just because of the demand and how you get the water back in the ground. I mean, you couldn't apply that commercially. Those are the 3 types of geothermal loops: horizontal well, the vertical wells, slinky pipes, pond water. And like I said, there are heat people out there making heat exchangers to drop in ponds as well.
I wonder if the drawbacks to those, the algae, things like that.
Well, the algae not so much, but the mussels.
Well, I knew that happened down on the river, yeah.
Yeah. There are some applications here in Little Rock that had problems with mussels covering up all the pipe. You don't get any heat exchange anymore.
Is it a problem with heating your pond though? In the
Well,
summertime?
They say in a pond that you ought to have at least 7 foot depth and so many acres per ton.
Okay.
And so there are design methods to use for ponds. But, I mean, if you're gonna do a pond in a commercial application, it'd have to be pretty large. I forget the, how many acres per ton, but, so they had series and parallel loops, vertical, horizontal, the coiled or the slinky. And the loop field conductivity determines your amount of loop. Right, the standard rule of thumb for a vertical well is 250 feet per ton. That's a rule of thumb. It can get worse or it can get better based on your conductivity. And the only drawback to this geothermal system is I might do a conductivity test today. 5 years from now, my water's been rediverted by something that's happened either geologically or construction or something like that. So there's some safety factor that you want to put in that. That goes up to about 375 to 500 feet per ton for horizontal in those 5 foot deep ditches. And in the pond applications, you just have to look at every one and apply.
But now, on your horizontal there, you get it pretty bad summer, and you don't get hurt like the drought.
Well, again, it depends on how much water you've got, but that's why they do more horizontal, because you know you're going to have less water. And so you're just extending that heat exchanger area out to compensate for that.
Yeah, I think that horizontal is what they mainly use in this area.
A combination of both. We tested our site here for a vertical well, but it was all sand and the well kept collapsing. So it's been very expensive to do it. So we attempted geothermal here, but weren't able to do it. Pumping systems, we talked about central pumping systems. You can also have that loop. A lot of people, especially in geothermal loops, you got a series of heat pumps. They'll put the little individual pumps on each heat pump. They might actually go to a well right back into the building. Generally, that's about the only time you put the individual heat pumps on the units. It's when you've got an individual drop in a geothermal application. For most water source heat pumps, you're going to use a central pump. Again, because these little bitty 2, 3, 4 gallon a minute pumps are 60% efficient. Bigger pumps get up to 80% efficient. It's like heat pumps for lowering water temperatures. Let's go ahead and stop here. And Thursday we'll get into some of the pipe